Hello students, in today's video we will see how to find particular integral for linear differential equation with constant coefficients. Okay, so this is our general linear differential equation with constant coefficients, nth order linear differential equation where all these ai's are constants. To get a particular integral you have to consider this equation. Okay, so here we are replacing d by dx by this uppercase D, so we get this one polynomial in D in this bracket operating on yp, which is equal to f of x. See, our aim here is to get particular integral, that is yp. So the solution of this will give us yp. We have already seen how to get complementary function yc, which contains all those n arbitrary constants. So yp particular integral, it is a term of the general solution which is free from all those arbitrary constants. Okay, so let's see how to get it. So this polynomial in D, let us call that as phi of D. So phi of D is this polynomial which is operating on yp, which gives us f of x. Now we want, so this, as a D is a differential operator, d by dx. Okay, so phi of D is also some differential operator. It is a combination of all these derivative terms, so it is also one kind of a differential operator. Now we want an inverse operator of this so that we can get this yp. See here, if you operate phi inverse of D, the inverse of this operator to the both the sides, we'll get yp. Okay, so we call that as that, we denote that inverse operator by this phi of D is equal to 1 upon phi of D, which is the inverse of it, such that when it is operated on f of x, okay, we should get a function of x which is a solution, right? Because when you operate 1 upon phi of D both the sides, we'll get, this side will be y of p and this side we get 1 upon phi of D operating on f of x. So now we have to see how this function, how this operator will act on this f of x. Okay, so this phi of D is a differential operator. So the 1 upon phi of D is also again an operator. We can call that as integral operator. Some kind of integration will involve, right? Because we want inverse of differential operator. So now we have to see how this actually acts on f of x. How this 1 upon phi of D will act on f of x, so that we'll get a solution yp which satisfies our these equations 1, 2 and this equation. So let us see one example here. We'll start with simple example and then we'll generalize it. So suppose you have to find a particular integral for this example, dy by d is equal to sin x. It is a simple, okay, very simple example. So d by dx is a capital D, so d of y is equal to sin x. Now we have to find y. So y is a function of x, okay, which satisfies equation 1. So let us solve this. Now see, as D is equal to, is a differential operator, we have to operate inverse of differential operator, okay, to get y, this y. So can you guess what that inverse of D should be? If D is a derivative, so inverse of D has to be antiderivative, right? So let us denote that by 1 by D. So when we operate 1 by D both the sides, see what happens, we'll get this 1 by D operates on equation number 1. Now because 1 by D is the inverse of D, here we'll get y, which is 1 by D sin x, but this y is nothing but yp. All right, so when 1 by D operates on sin x, we must get a function of x which satisfies equation number 1. Okay, and we know that what is the solution of this equation has to be, it has to be a minus of cos x, right? You can see here derivative of minus of cos x. What is derivative of minus cos x? It is a sin x. Okay, so what you understood here, so 1 by D of sin x is nothing but minus cos x. That means 1 by D of sin x is what? It is integration of sin x dx. Alright, so 1 by D behaves like integration only. If D is a derivative, 1 by D is integration, simple, inverse of derivative, right? So this is how it works for the simple example. Let us consider one more example, then it will get clear. Suppose you have this example, dy by dx plus 2y is equal to x. Okay, how will you solve it? But see, this is linear differential equation, okay, we can solve it easily. Okay, so d plus 2 of y is equal to x. Then now we have to operate inverse of d plus 2 again, okay, to both the sides of equation 1 to get y, which will be divided by yp. So apply 1 upon d plus 2. Let's call 1 upon d plus 2 as the inverse of d plus 2. So we'll get this, correct? Now this d plus 2, this will become 1, right? It is not because this d plus 2 and this d plus 2 get cancelled. It is because they are inverses of each other, and therefore it will become identity function 1 by d operating on d plus 2 y. Okay, so 1 by d and this d plus 2, that will become, so it is a composition of two functions, operators, and the composition is identity. So that's why here we'll get y is equal to 1 upon d plus 2 of x. Now, but how to evaluate this 1 upon d plus 2x? Okay, so the first one, as we have discussed, is linear differential equation. We can easily solve it. Its integrating factor is e raised to 2x, and general solution is this: y into e raised to 2x is equal to integration of e raised to 2x x dx plus c. Now integrate it and divide throughout by e raised to 2x, so we get this: y is equal to e raised to minus 2x. So see, here we are not integrating, okay, we are keeping that term as it is. We are just divided both the sides by e raised to 2x. So we got this term: y is equal to e raised to minus 2x integration of e raised to 2x x dx plus c into e raised to minus 2x. Now look at here, we don't have to worry about this part, c into e raised to minus dx, that we already get. Okay, we can get this part by finding complementary function, which I already seen how to find complementary function. Okay, so here now you can see that 1 upon d plus 2x, okay, has to be what? This first term, e raised to minus 2x integration of e raised to 2x into x dx. Okay, so this is how 1 upon d plus 2x, 1 upon d plus 2 operates on x. So here we are multiplying by e raised to minus 2x. So you can see here we have d plus 2 and here e raised to minus 2x. So for d plus 2, if d plus 2 is a factor of our auxiliary equation, its root will be minus 2. So that minus 2 is here, e raised to minus 2x, and integration of e raised to 2x. So we have d plus 2 and the same 2 is here, e raised to 2x, and this is our function x dx. So this is how 1 upon d plus 2 operates on x. Alright, now I guess you have understood how this works. Suppose we have, instead of d plus 2 we have 1 upon d plus 3, so how it will act on this x? We'll get e raised to minus 3x integration of e raised to 3x x dx. What if we have, instead of d plus 2 we have suppose 1 upon d minus 4 operating on x? In that case it will be e raised to 4x. Okay, when we have d minus 4 here, the root will be 4, so e raised to 4x integration of e raised to minus 4x x dx, like this. So in general 1 upon d plus m f of x will be what? So here we have d plus m as a factor, therefore root will be minus m, so it is e raised to minus mx integration of e raised to mx f of x dx. Don't put c after this, alright? The complementary function will take care of that arbitrary constants, so we don't have to worry about arbitrary constants. We are just finding a solution which is without arbitrary constant. So this is how 1 upon d plus m operates on f of x. Now in general, when we have yp, which is 1 upon 5 of d f of x, so if we have these are the roots m1 m2 up to mn, these are the roots of our auxiliary equation, then yp will be 1 upon this into f of x. This is a factorization of 5 of d. Then how to solve it? So there are two methods. In the first, you can apply one factor at a time and continue like this. So first we'll operate this 1 upon d minus mn on f of x, and then we'll, after solving this, we'll get some function, let us call that as f1x. Then same method, this remaining term we have to operate on that f1x, and so on. You can continue like this, or other way is by using partial fraction, we'll separate all these terms. Okay, so we'll get a1 up into 1 upon d minus m1 operating on f of x, plus a2 into 1 upon d minus m2 operating on f of x, and so on. So there are two ways, either we can use the first one or the second one. The second one you cannot use every time. There are some limitations. For second one, these roots should be distinct. When we have repeated roots, we have to use this first method. Only for those repeated roots we can use the first one, and the roots which are not repeated, okay, single roots or simple roots, for them you can use the second method also. So this is how we can find particular integral for given differential equation, and this method is called as a general method of finding particular integral. In next videos we'll see there are some shortcut methods also which you can use to find general solution, but this method works for every example. All right, I hope you have understood this. Try to solve some examples on this. Thank you.